Welcome everyone to this week's Autonomy Talk. This great week is a great pleasure to have with us Professor Cosimo Della Santina, who is an assistant professor at TU Delft and also a guest scientist at the German Aerospace Institute, also known as DLR. Something about Cosimo. Cosimo got his PhD in robotics from the University of Pisa, and then he was a visiting PhD student and postdoc at MIT's Computer Science and Artificial Intelligence Lab. And also he spent some time as a postdoc and a guest lecturer at the Department of Informatics at the Technical University of Munich. Cosimo leads a lab at TU Delft, which focuses on the study of embodied and disembodied intelligence in physical systems. And the emphasis of the group is on elastic and soft robots. As you've seen from the bio I shared, he has won a number of awards. I will not list all of them. Maybe the most recent is the 2023 IEEE Early Career Award in Robotics and Automation. And he's part of many exciting initiatives in the Netherlands. Today he's going to talk about controlling soft robots, a mostly model-based view. And I'm very excited to hear more about this subject and to have this subject covered in this Autonomy Talks series. So without further ado, Cosimo, whenever you're ready, go ahead. The stage is yours.
Great. Thanks for the kind introduction, Joel. Please, to everyone online, just feel free to interrupt me if you have any questions that you want to discuss while I speak. So, what do we do? Joel already mentioned a good part of it, but we look in low-level intelligence. It's of or arise from non-conventional mechanical systems and beyond, more in general, physical systems. So from a very high level, but fundamental point of view, this means playing with the dynamical systems, which have some kind of combination of their behavior being kind of dominated by some form of potential energy, they are usually high dimensional, and they have some kind of rich or useful autonomous behavior, autonomous evolution, which is one of the way you can describe or quantify this idea of embodied intelligence. And in terms of applications, this goes through all over the spectrum, more or less. These are some videos taken more or less randomly from works that we do. This one is not started. Yes, that I will not be showing today. In terms of application, indeed, our activities cluster around these three macro topics: so robotic hands grasping and manipulation, soft robotics and elastic and soft quadrupeds, and efficient locomotion. And today I'm going to talk mostly about soft robotics. And what soft robotics means, it is kind of a debated topic. This is a definition that I gave together with Mane Catalano and Antonio Bicchi. So since I gave it, is the one that I liked the most, or at least I liked the time in which I gave it. I will implicitly refer to soft robots as this second half of the spectrum, left half of the spectrum, which is continuum soft robots. And these are robots inspired by invertebrate animals mostly, whose body is composed in a good part, for a good extent, by continuously deformable materials. And over the years has been quite active research. I mean, this is a topic that has its roots in the 80s, but it had quite a steep increase of interest in the past, let's say, 10 years, more or less, with a lot of platforms, hardware platform being developed, and you can see just some random collection of them here, mostly from others' labs. And the goal in all these cases is to hopefully get closer to the kind of intelligence which is most common in nature. So, as we all know, robots have been for many years much more precise than humans or other animals in performing tasks, but still animals are more robust in interactions, safer, and compliant. They can be both precise and compliant. So interaction tasks, robustness, so in kind of inspection tasks should be the way to go. But if you look then at what happens in reality is that for several reasons, rigid robots still outperform soft robots in the very tasks for which soft robots have been developed. So interaction and inspection. And there are many reasons for that. Everyone has their favorite reason. My favorite reason is motor intelligence. So the lack of efficient and effective enough low-level brain for this kind of artificial creatures, some way of making sense of their own bodies and control it to perform actions. So we look into this with our group, and I will briefly discuss the main our general view on the topic. But before starting to lay it down, I want to clarify that the way in which we look at this is really to kind of very classical in a sense control theory point of view. So we really started from the theoretical foundation, then trying to build upon of them new algorithms, and then in the end upon them new functionalities to really give software robots intelligence. And now I have finally videos of experiments to show, but this came only after a few years of intense research, more on the theoretical side. And indeed, this is the list of the things that I'm going to discuss as a map of the talk, and it's kind of quite classic division in terms of modeling, regulation, beyond regulation, and then a bit something more if we have time. And of course, we talk about model-based control, meaning more than model-based, a model-based view on the control problem. So we need at least to clarify what we mean with models of these systems. And myself, I'm not an expert in modeling, and I will not say that we do modeling of this, or our core expertise is modeling. But what I find particularly interesting is trying to figure out what is the structures of this model. So not necessarily come up with the best or most interest or most accurate models, but trying to really dig into the mathematical structure of them and trying to understand what are the commonality among all different already existing techniques to discretize these systems. So why modeling is hard? It's hard for several reasons, but there is a core fundamental reason, which is the fact that if you have a software robot like the one that you see in this picture, in this video, and if you want to already start just telling where the robot is at a given instant, you have to specify, and already if you add some assumptions that they will not go into, you need at least to specify a complete function, so which is the spatial curve that let's see if hope you can see my pointer, spatial curve that defines the position and orientation of each point of the backbone of this robot. So this is a function that evolves in time. This means that at least in theory, you should be using a partial differential equation to model this system, which is very hard to deal with. And this is something that we don't like. And especially from the control point of view, the theory, it's relatively limited on them. So what we like the most is to do some kind of space discretization, which is done in such a way that you end up with ordinary differential equations in a structure that you like, and then we are used to play with or deal with as control or people working control of mechanical system or robots. And the key point of this space discretization should be that if you take the order of this discretization to infinity, so you make it very, very fine, and infinitely fine, then you should be recovering the original system, because in this way you get at least some kind of weak proof of convergence on the original infinite dimensional case, if you prove things on this finite dimensional case. So contour-oriented models, derivation tiny nutshell. So what are these kind of models, yeah. And in the end, coming up with such models can be to the bone, described in 2 steps. So the first one, which is kind of a key step, is to define your knobs. Meaning that let's consider, for example, the shape. You have a shape of this soft robot, which is this thing here. And already if the soft robot is forced to move on a plane, so 2-dimensional space, you already have a function that goes from 0 to 1, so some kind of local. So this is the domain of the function is 0 and 1, because this is the local coordinate. And then for each point S, you have to specify X, Y, and alpha, so the whole position orientation of each point. So these are 3 functions that specify the shape of this thing. What you need to do is to somehow come up with a kind of mapping between a low dimensional or a finite dimensional amount of variables that you move, and if you move these variables, this will define some kind of movements in infinite dimensional shapes. And this is really where all the art is. So define this kind of a forward kinematics is the art is, because it's where the expert intuition enters. And yeah, and I will show in a second a few examples of these. But once you have these knobs, then you can you have ways in which your robot can move, and you have associated movement of mass, and then you can just actually use a standard, quote-unquote standard Lagrangian machinery to come up with your ordinary differential equations. So, and these are going to be equation that describes the evolution in time of these knobs, not of the infinite dimensional system. So what are these knobs? One we have been looking, I think it's quite nice, is to do this kind of a fine discretization in curvature space. So you take the curvature of this curve, and you parameterize this as an affine function. And what you are seeing here is the effect of, so these are 2 degrees of freedom in the end, Q1 and Q2, and you are seeing on the right the local angle along this soft robot, and how this change when you are changing these 2 knobs, Q1 and Q2. And you can see that with just 2 degrees of freedom, you can obtain quite complex shapes. And this one on top, we are keeping Q2 equal to 0. We are changing Q1, and this is called the constant curvature segment. And this kind of constant curvature segment actually is grounded in a much more classic ideas, which is called piecewise constant curvature model. And here you have the knobs are again you are looking at your soft robot as a interconnection of circles with constant length, but with variable curvatures that it's variable in time, but it's constant in space. So each knob is associated to the local curvature, which means the inverse of the radius of this circle, of each of these local circles here. And this works particularly well for some reasons that I will not go into, to describe systems that are made by interconnecting actuators, so soft actuators. You can see it here. The core idea: you have this soft robot, and you can identify parts in which the shape will more or less look like an arc of a circle, and then you just combine these. And again, with each knob, you are going to change this angle here. So in the end, to take home message of this idea, first one, it works. And you can see here in some examples of few works that we have done of modeling soft robots, the dynamics of soft robots, using this very low dimensional model. So these two here on the bottom are two-dimensional, so 2 degrees of freedom. And this one, I always forget, but these are it's 10-ish degrees of freedom. So this is a tendon-driven robot with a heavy mass on the tip, and this is a tentacle of silicon moving in water, and it's you have the motor here on the tip, which is exciting this motion. And this one, it's instead is a robot made of metamaterial. This is a collaboration with Daniela Rus at MIT. And yeah, I think it's remarkable that you can obtain, represent at least a good part of these complex movements with such a small amount of degrees of freedom. So, but a bit more formally, since I see it's already 15 minutes that I'm speaking, what we are more usually dealing with are this kind of ordinary differential equations, where you can identify 3 blocks of terms. One first block is more or less standard. If you have been working on control, or looked in control of a mechanical system in the past, or classic robotic system, this is what you usually have. What you have inside for software robot is different, but the structure of the equation is the same. And then you have this effect of softness, and this is a dissipative and elastic potential field that permeates all degrees of freedom, regardless of the level of discretization, and ends up acting as a stabilizing effect, which helps you. Then you have this model of under-actuation. So you have to have some way to map your finite amount of degrees of freedom, of degrees of actuation, so of inputs on the degrees of freedom, and this can be done usually, in most cases, with a matrix. Since this is a quite important point, I want to look a bit more into this. So this is a soft robot with 2 actuated with tendons. Let's assume that the tendons end here. This means that you have you can pull them, and so you can generate these 2 control actions, and you have these which end up in this tau here. And then it's up to you how much finer you discretize this robot. But for example, if you use a constant curvature model, you use 3 constant curvature segments. These are 3 arc of a circle here. Then you end up, these are quite a rough approximation, but still you can describe the shape of this system. And you end up with a 3x2 matrix, so 3 degrees of freedom and 2 degrees of actuation. If you add another actuator, for example, if you add another tendon that pulls your robot here, then you will end up with a 3x3 matrix. But then if you start saying, oh, I want to a finer approximation, I want this to work a bit better, than what you will end up with is a taller matrix or something like 6x3. And there is no limit to that. You can then get it finer, finer, and finer. And in principle, you will get to kind of infinity by 3. So infinitely long vector with columns with 3 rows with 3 columns. And the same holds for all other parts of this dynamics. You have this spectrum, which you go from kind of a fully actuated model, which you have same amount of degrees of freedom and degrees of actuation. And if you bring n to infinity, you will increase the dimension of this vector and the dimension of this K matrix and the dimension of Q, ending up with infinitely big matrices. And this is true for all the matrices and vectors in the dynamics. So this is nice because it solves the general thing that we need to start talking about motor intelligence from a model-based perspective, which is this kind of model space discretization, which is finite with a finite amount of degrees of freedom, but that in a sense it's a good representation theoretically of the infinite degrees of freedom case. But it's not this kind of discretization is not great actually for control. Why is not great for control? Because you have this full matrix A, and this full matrix it tends to end up mixing all the control inputs on all the accelerations, and so it's very hard from the control point of view to disentangle things and end up controlling the system. So, for example, it's not even clear what it means to do collocated control in this context. So this is where kind of higher order magic enters into play. So before we had the first level, which is discretization. So the fact that you can look at this infinite dimension as a finite dimension. And the higher order is actually involve no approximation, and it's a change of coordinates. So it's something that we have been thinking for a few years, and my guess was always, the answer of this question was always no. And the question is, if you have something like this set of equation and you have this matrix here, which is full, can you just by means of a change of coordinates end up with something like this? So something which you have a clearly separated a set of equations where your actuators are acting and all the others are passive. Let's see. And this way you have a much more clear connection between the inputs and the actuated coordinates and the unactuated coordinates. But the answer is yes, and yeah, maybe a quite technical request, but anyway, it's an if and only if. We're very happy about it. This is the integral of the passive output of the system, and yeah, let me not go into this, but I think what is quite remarkable of this is that then the change of coordinate is on the actuated side. So the set of variables that are actuated are indeed this result of calculating this integral, but all the other variables can be whatever you want. And then regardless of what you put there, you're still going to have a zero there. And this is something that took me a long time to believe is a result of Pietro Pustina, a PhD student in my group. But it's true in the end. So he managed to convince me. These are the questions we end up with, and we call this actuation coordinates or collocated coordinates because you can give a very clear interpretation to Q of A, and these are the configuration of the actuators. And I will provide an example in a second. And all these others, you can just take just n minus m variables from your original body coordinates, and it will work. But now you will have this very nice structure of your equations. So an example is available here. You have your tendon-driven soft robot. So this is your soft robot. You have 3 tendons, and this is the input matrix. You just have to believe me that this is this nasty one. And if you integrate you can solve this in closed form for Q1 and Q2. You get, again, this very nasty thing. But what it's important, and these three variables are going to be the actuated coordinates of your system. And these are exactly the tendon displacements along the robot, or alternatively, the scaled angle of the three motors. And this is described in this paper. Again, it's a if and only if. It's been very recently accepted by TRO. So just take a look if you're interested in the nitty-gritty. But this is the final picture in which we are, at least at the moment. So you have this first phase in which you discretize the system, so you approximate it, and then you have this set of body coordinates in which that you get from the discretization. These are cool because of what we have discussed, but then from them you want to go in actuation collocated coordinate, because it's where then the control is possible. So it's kind of this two-level step, and these two are actually equivalent, while both of them are an approximation of the original system. So we are happy here, and we can move to probably more interesting things, which are what you actually do with these things. So how you use them for control. And yeah, this is an example. You want to have some kind of motor intelligence. You have your actuators, you have a set of sensors. You have a desired behavior, you want to impose it on the system. And the simplest kind of control problem that you can think of is a shape regulation. So you have this reduced amount of actuators. We assume a full state information. You have a desired shape, Q bar, and you want to close the loop so to obtain that desired shape on the software robot. And hidden behind all things that I'm going to show, at least then in the experiments, there is this fact that you have to come up with some kind of shape selection, which is another place where the model is extremely important, but I will yeah, I will not have time to discuss that. So you have to select somehow a shape that is an attainable shape, and so can be indeed obtained, and that fulfills your goals. So let me skip this. In order to solve this task, we realize quite quickly that this there is no solution, like no one fit all solutions. You have to start creating this taxonomy of fundamentally different behaviors of soft robots, and for a good part of them, you can live with collocated control, and this is what we have been doing for the most case, and only for the more advanced case, which are really soft or very nasty input things, then you have to resort to not collocated control, which I will not discuss about. Collocated control, how does it look like? Of course, you can, I mean, we have also looked into this more hard, or let's say, the usual things like feedback linearization, things like that. But in order to then make it work on a real system, then you have to kind of come and think of something which is, in my opinion, simpler. And this is usually more complex to design from fundamental point of view. And this is in general a good general description of the kind of controllers that we have developed. One is a PID that closes the loop on the collocated coordinates. So this is a PID on the motor side. And this is indeed what people have been doing for the 10 years. So people that didn't care about the model, just wanted to make to show off the robot moving. What they were doing was just close a loop on the PID side. And this is what for a few years I have been saying, this is bullshit, you should not do it, you should control on the body coordinates, but then I realized that it was actually a quite good idea. Took me some time, but this is a PID that people have been doing even before. But this part is extremely important, and it's the compensation and cancellation of most of the potential forces, and this is necessary actually to get to steady state or good steady state behavior. Is the fruit of research in model-based regulation. And this is a block schema of how this would look like. So this is what people have been doing before. So you kind of close loop on these actuated coordinates, but then you have you hope that this unactuated dynamics, this kind of internal behavior, internal oscillation will not kill you, will not stop the thing from working properly. And instead, what we propose in the end is to add this extra loop to that, which explicitly accounts for the effect of unactuated dynamics. So this is an example of such a controller. So for example, a PD with this kind of feed-forward compensation of elastic term and feedback compensation of gravity. And yeah, the trick is usually that to prove these things is to rewrite the closed loop in such a way that you ending up using the physical dissipation and the physical elasticity of your system as a stabilizing effect, as I was mentioning before. And then you have to show that this is strong enough to kill or survive against the destabilizing effect of gravity. And we have, as mentioned, variation. We have not time to go into them. What it's more relevant is to start and see if this variation actually work. And so to have some nice reality check. And this is a part that I'm happy to have, because in not long ago I will have stopped my talk here, which would have been better for time, but not for yeah, my personal happiness. So now we have a few, we are at the point at which we can bring these algorithms on the real systems and show if they work. And this is a 1 degrees of freedom. These are ongoing experiments, actually. So this is a 1 degrees of actuation system. So it's just a passive piece of silicon, which is controlled with 2 motors, with, let's say, 1 motor. And then you can discretize this with n degrees of freedom. And this is 2 degrees of freedom in the picture. So you can see the reconstruction overlaid there. And we have a motion capture system to close the loop. And Pietro is downstairs at the moment performing literally tons of experiments. They have been ongoing for weeks now, and where you just test these controllers, and we're actually going for even more of them in a lot of different trajectories or step response. So I don't have therefore a global or final result of this, but there are already some interesting trends that comes up. So one is the performance of these controllers with respect to the level of discretization, of the kind of discretization. That what it seems to quite clearly arise is that even for such a very simple system, you have to keep into account the underactuated dynamics. So the underactuated part. So if you use just 1 degrees of freedom for 1 degrees of actuator, you get almost 1 order of magnitude more error. While at the same time, it appears to be that, again, for such a simple system, there is no much benefit in increasing the order of discretization. So 2 degrees of freedom are actually enough, and there is also not much benefit in using more smarter discretization techniques. So this is a comparison instead of steady state error for vanilla PD, vanilla PID in a sense, and then a PD plus, so a PD with these regulations error, and as for different proportional gains, as you expect, as in terms of steady state behavior, the PID works better, but the PD plus works, I think, reasonably well as well after if you have even a relatively small gain, you will already get comparable performance and much better than a PD. But it's more, I think, in my opinion, more interesting is that if you start to look into the control actions and into the transient, you see that even if the steady state is looks nice, the control action of the integral one, which are these, for example, these blue ones, and this transient, these yellow ones are quite bad. So for now, according to preliminary analysis, probably to some cherry picking, the PD with the model base one works better than the model free alternatives. More to come. Another system we are playing with is this is in collaboration with DLR. It's system that you have no way of model as fully actuated because you have an explicitly passive part. So you have this part is actuated and this part is explicitly passive. And I will just show you some videos of application of our controllers to do tip positioning of so basically you have 4 motors here and you are pulling this tendon so to bend the base part in such a way that you can position the end effector as you like. And this is other work on from Maximilian, who is here, I think, here he looks into closing the loop on this very fancy and nice robot that people in Daniela's group have developed. Yeah, Ryan Truby, Jeff Lipton, and Lilichin, and this is based on metamaterial. The inputs are control action of these motors, and this is the setup that we just quickly go through that. But what I think it's nice is to see the level of precision that you can get even with such a complex robot. You are able to track quite precisely these plots. And this is yet another recent result. Is called Helix, and this actually goes beyond the control part. Is a new robot that we have developing together with Josie Hooks and Francesco Stella at PFL, and Francesco is thinking of building a company out of it. So if you want to know more, just follow this QR code here. But again, you can see how using these advanced controllers we have developed, you can end up performing tasks which are quite while maintaining the compliance of the robot while being very precise. This is about shape regulation. So I had a whole section beyond regulation, so for trajectory tracking, but I think I will just completely skip it. To go here, because I really want to show the final part, and the time is already up. So yeah, for the soft robotic part, we have seen some example of nice thing. I just want to show maybe a few videos just also on this part to motivate you. The fact that there are we have realistic, not realistic maybe, but validation of controlling and giving a motor intelligence for this complex system, but is there is really a lot to do still to really get reliable performance. So in practice, you end up sometimes having this unstable or reduced performance behavior, and this is something that really needs further theoretical investigation on one hand, and even more and more real-world applications on the other. Many of these things are discussed in this tutorial/review paper that we have written together with Christian and Daniela, and it appears on the Control System Society magazine in a special issue on soft robotics that Helmut Hauser organized. So I think we try to write it as a kind of a tutorial paper for this model-based view to the problem. And I want to conclude with some outlook to something more, something beyond shape regulation and shape tracking, and 2 points in particular. So one is about machine learning. So usually when I end up talking with for 1.5 hours for this about models and model-based control, one question that I always receive is why not just using machine learning? Because it's why bothering going through all this trouble if we are seeing that directly learning works very well. And I am all in favor of using machine learning. I do that for other systems in other contexts, but in this context, I think one direction I'm very excited about is the fact that recognizing that models do not need to be first principle models. So models could be learned as soon as they are learned properly. And this is work that we have recently done, has been online for less than 1 month, published for less than a month, I believe. And the idea is to learn from data a dynamic model, which has the structure that we know is going to be the structure of the real system. So again, we come back to the fact that it's not really important how you end up with that model, as soon as you understand what are the structural properties that it needs to have. And then you deploy this learned model on a provably stable model-based controller, which is developed using the theories that I discussed before. So we use a Lagrangian or a Hamiltonian neural network to do that, which are a bit modified to get to good to work on soft robots. And yeah, we have validation on soft robots. You can see here. But the thing that excites me the most about this is not just that it works, but also the fact that you can really give guarantees at this point. So you can start plugging the control based on the learned model in the real model, in a sense, and start to reason on the stability of the closed loop in presence of not perfect learning behavior. And again, the performance are pretty good. This is not a soft robot, but it's I think it was important validation, because it's a low level we are using to replace the low level control of the Franca Panda robot, and we get comparable performance to the one that engineers came up with, I guess, with working a lot on it, and this we can directly get it using this pipeline. And other works going in these directions are ways of deep learning based ways of compressing high-dimensional dynamics of these soft objects, maintaining again their Hamiltonian or Lagrangian structure, and again using them as a base to close the loop. In this case, we have only results in simulations. You can see here on the right. And similarly, this is another work in which we directly learn these models from streams of RGB data. So this is one end. Models do not need to be models, in the sense, not need to be first principle model. But another thing that we are looking into is the fact that software robots do not need to be software robots. And what this means is that you can take a kind of something like this classic robotic manipulator, and one reasonable task to solve with this manipulator is to manipulate a deformable objects with non-negligible dynamic response. And this is actually not what most of, at least in the model-based solutions, have been in manipulation of deformable objects to look into. But I think it's a very interesting use case, and this is, for example, comes with from a collaboration that we have with a company. But this is a heavy electric cable for recharging cars, electric cars, and you can see this. So this is more evident in this simulation. You can see this as a kind of a hybrid soft rigid robot, where you have the soft robot, which is completely passive, and it's the object, and the rigid part, which is instead active. And you can apply, as it is, all the theory that we have developed or discussed so far to this new context. Yeah, first of all, for modeling. So this is the result of the system identification of when you see the model prediction overlaid on the actual behavior of the system, on the soft part of the system. But then you can use it for closing the loop, for control. And we consider here a quite academic task, but still interesting. So to position the end effect, so the end of the soft part. So you want to position this kind of plug part, so this last part in space, so position and orientation, and you end up computing the statics and then closing a collocated control loop to end up with this point in some position and orientation. Yeah, and this is the comparison between the expected performance from the model and the actual, the real one for several desired location. And in general, compared to like a vanilla strategy, you can, which you just move the thing to go on top, you get a dramatically improved performance by doing this kind of model-based closed loop version. I think this is quite evident if you start doing things like this. For example, here we are trying to position this connector in the same place in space, but so same position but different orientation, and then you end up with this kind of nice behaviors, nice behavior in the end. And yeah, this is just simple, not really meaningful from an application perspective, but I think interesting other kind of capability that you can obtain. So very precisely move and put this hook into this circle in the hook. So this is a paper, if you want to take a look at it, it's online. And this is now really it. 7 minutes late, and these are the people that are actually doing the work that I got to present. So a big thanks to them, and a big thanks to you for attending.
Thank you, Cosimo, for the great talk. A lot of interesting stuff from different domains and perspectives. Let's open the stage for questions. you can either type in the chat and I will read, or you can directly ask, raise your hand and ask. Maybe I'll be the icebreaker. So I have different questions maybe about the details, but here I think a big question for me, or a big interest for me, is the role of design in all of this. It seems to me that depending on the tasks you want to solve, you might design different robots, and the different designs will create different complexities when designing controllers
Yes.
and so this idea of having very nice models, or the recent ideas you presented of having model-free versions or learned models, and the idea of having a flexible design is really interesting to me. And it feels that in soft robotics, this is really much more important than in other systems, right? It really influences how you will control your system, how efficient your control actions will be, and so on. What's your? I know it's not really a question; it's a bit of a general
it's actually it's actually a central point. So thanks thanks for asking. It also gives me the opportunity to discuss a bit on it. So I started a talk with this picture, and you maybe have now understand more or less why it was talking about potential energy, high dimensions. But there is this aspect I really didn't touch upon, which is the richness, usefulness of the autonomous evolution. So this open loop behavior, and this is kind of this part that comes from the design, right? So you have this the fact that soft robots, or in general elastic robots, have a kind of already embodied intelligence, and kind of open loop behavior that is already nice, and it's central to understand how you design them. So in the talk today, I was reporting our results on trying to at least start by putting these robots in a more familiar context, which you can start really to talk about what they do, from using equations and assess things. But I definitely think that that's the way forward. So to try to then use this framework to understand how to engineer these autonomous evolutions such that they behave nicely. And on that hand, these are some of again the paper things we are working on, and I think of all of them, the only relevant is this one here. So I've been looking into the problem for elastic system. So system are more like articulated soft robots are sometimes called. So you have more joints, but then you have elasticity at the joint level. And for them, what you see here, it's a system is a leg with softness or elasticity at the joint level, and this elasticity is optimized so to get this jumping motion in open loop. And so what we do is that we then design some kind of controller that excites this natural oscillation of the system, and then it's just the actual physics. So you can see it's quite a nice jump, or a compliant jump that are obtained. And this we started to do, or I was doing for articulated system, because there was clear what it meant to solve this task. But hopefully it's some of the things that I presented can be used in a more general context to do similar things for soft robots.
Yeah, that's great. That's a great line of research. It's really nice that soft robots could be a nice test bench for these new approaches that try to mix design and operation,
Yes.
right?
Yes.
Very nice. Thank you.
Indeed.
And is there any other question for Cosimo? Yes, Tongja, you have a question?
Yeah, yes. Hi, Cosimo.
Hi.
Yeah, I have a question. At some point, you talk about we need to make sure the desired shape is assignable, right?
Yes.
And what if I just give it a configuration that is unassignable? What will happen to your theoretical proof, and what will you observe in the experiments?
Again, thanks, Tonya, and also nice to see you. Yeah, this is another question that gives me the opportunity to clarify things I didn't have time to clarify. So you are, I think, referring to this picture here. And I mean, there is this caveat of the fact that since you have a finite number of actuators and a theoretical infinite amount of degrees of freedom, you actually cannot implement or generate all possible shapes. You have to, you are constrained, at least a steady state, you are constrained by a manifolds of shapes, which is of the same size, at the best of the same dimension of the amount of independent actuators that you have. You can come up with this some kind of inversion to come up with this desired shape. But what you ask is that if this inversion is not going to be precise, or in general, if you are just trying to destabilize my system and you just come up with as input something which is completely different what the robot can do, what will happen? And the answer is that I don't know. So I don't know in the general case, because it's something that in terms of formally proving what will happen is something we still have to do. It's something on our list for the future. But it's in general, I expect if you have this kind of controllers, let's consider this one for example, where you have a PD, then you have a feed-forward action for the elasticity and a feedback action on the gravity. I'm quite confident that you can rearrange your proof by just saying, okay, you calculate the other equilibrium, because the equilibrium is not going to be your Q bar, it's going to be something else. Let's call it Q double bar. And then I would expect a similar condition around this Q double bar apply in order to get stability. So in the end, you will have similar condition for stability, at least for this kind of controllers, but you will have some steady state error, because you cannot get there. You will just, your controller will just try to bring you close to that. This is for this simple controller, but then when you start to add in a kind of integral actions or feedback actions on the elasticity, then very bad things can happen. And this is definitely yeah, because for example, for the integral part, you will never be in a condition in which this difference is zero, so this will go to infinity. So yeah, long story short is one of the next steps that we would like to look into. So that's a very good question.
Yeah. May I have a follow-up question? So in your answer, you also said if we have m degrees of input, then the assignable may be a m-dimensional manifold, right? Is it a theoretical result, or it's a hypothesis?
It's a theoretical result, but it's unpublished.
Oh. Okay.
So, but yeah, I mean, it's not unpublished in the sense that it can be shown actually quite easily if you put yourself in this actuated coordinates scenario. But I've just never written it down explicitly somewhere. It's going to be in a paper that I'm writing, but it's not available now. And it's a direct application of the implicit function theorem.
Okay, I'll look forward to seeing that. Thank you.
Thank you.
Thank you, Tongja, for the questions. Is there any other question for Cosimo? Maybe a final one? Okay, doesn't look like it. I think you left your email in your first slide or last
Yes.
slide for, oh, there was even a better one, a QR code.
Yeah, there is even a QR code, so you have you know
Exactly.
how to
So
get how to find me.
exactly. So feel free to reach out to Cosimo for deeper questions. Thank you very much, Cosimo. Very exciting. I look forward to seeing where this goes.
Thanks, thanks, Joel.
And we'll share the video once I edited it.
Great. Thank you very
And
much.
thank you everyone for joining. See you all next week for the next Autonomy Talk.
Thanks for joining. Bye-bye.
Bye-bye.